Good afternoon, everybody. Good afternoon, Sanjay.
Good afternoon to you, Thomas. How are you?
Very good. I'm looking at the clock. It is now 3 o'clock, and I suggest that we begin. So, dames en heren, ladies and gentlemen, geachte collega's, dear colleagues, I hereby formally open this session, and I'll welcome you all to the public defense of Mr. Sanjay Sekaran. Mr. Sanjay Sekaran has presented to the faculty his PhD thesis on the topic Deliberation, comparing the observational and theoretical parameters of binary systems with pulsating components, in partial fulfillment of the requirements for the degree of PhD in Science, Astronomy and Astrophysics. He shall now publicly defend his PhD thesis. Mr. Sanjay Sekaran, you are invited to give a presentation of about 45 minutes about your work. Afterwards, the examination committee will ask questions and discuss your work with you. I now give the floor to Mr. Sanjay Sekaran.
Thank you very much, Thomas. I will share my screen. So, can everyone see my screen? Well, I hope so. Well, good morning, good afternoon, good evening, wherever you are in the world. Welcome. My name is Sanjay Sekaran, and today I will present the culmination of the 4+ years that I have been working on my PhD thesis entitled Liber Stellae, or the Book of Stars. It has been my great honor and privilege to work under some of the brightest minds in stellar astrophysics, my supervisors, Andrew Kachenko and Connie Arts. So to my Indian friends and family, I say, Vanakkam. To my Dutch-speaking friends and colleagues, I say, many dank jewels for joining me today. And without further ado, let us move on. So in this presentation, I will give a general introduction where I will introduce the topic, I will introduce the relevant terminologies and the stellar objects of import for the understanding of the rest of this presentation. I will then go on to present my own work in the context of the currently existing literature. I will then move on to discuss the results that are in my thesis, and then end the presentation with a short summary of what I've discussed and potential for future work in the direction of my research. So let us start with a general background. But before I do so, I would like to give a bit of a public service announcement, because when we talk about stars in general life, the stars that we end up talking about are what I would call terrestrial stars. And these stars are, of course, much more applicable to you and I, seeing as they are, in fact, human beings. These stars include movie stars, YouTube stars, Instagram stars, and how do I put this? Stars that you don't really talk about in polite company. Those kinds of stars, terrestrial stars. Interesting as they are, unfortunately, we will not be discussing such stars today. The stars that we will be talking about today are the celestial stars. You know the ones, those tiny pinpricks of light in the sky that make us look up and gaze in wonder. And this is a special treat for you guys. There's also a third class of star, the enigmatic superstar. Some people say that it is both terrestrial and celestial. I don't know how this is really possible, but unfortunately, again, we will not be discussing such stars. So it's important to know the difference between terrestrial and celestial stars, else you end up doing a PhD in the wrong field. Take it from me. So, what is a star? What is a celestial star? Well, a star is a massive ball of gas that has begun to collapse under its own gravity. Now, this can happen for a variety of reasons, one of which is that a cloud of gas that is minding its own business, floating around in space, gets hit by the shock wave of a nearby supernova. It ends up forming local overdensities, fragmenting, and forming stars. The only thing that is keeping a star from collapsing in on itself completely is the gas pressure. Now, where does this gas pressure come from? Well, as we all know, stars fuse hydrogen into helium and other heavier elements in the cores or in the interiors of these stars. This fusion generates heat and energy, and this causes the surrounding material to heat up, and therefore gives it the pressure that prevents it from collapsing in on itself. So this counterplay of self-gravity and gas pressure is known, and this state of equilibrium between these two forces is known as hydrostatic equilibrium, and it is the state in which stars remain for most of their lives. So we know what a star is. There are many different varieties of stars, and these are displayed in this so-called luminosity versus effective temperature diagram, also known as the Hertzsprung-Russell or HR diagram. In this diagram, you can see that the effective temperature, in fact, goes from right to left and not the other way around, and the luminosity or the brightness of the star increases vertically in a logarithmic scale. The stars that we are going to focus on in this talk are these ones in particular. These are low to intermediate mass main sequence stars. And the main sequence is thusly named because stars spend most of their lifetimes on the main sequence. These stars are burning. When I say burning, I don't mean literally combusting in oxygen, but literally fusing hydrogen into helium in the stellar cores. And these stars are fusing hydrogen into helium, and they will continue to do so for about 10 billion to about 10 million years, depending on the mass of the star. The other category of stars that we're going to focus on are the so-called giants. These are often also referred to as red giants because they are reddish in hue. These stars are also burning hydrogen into helium, but they do so in a small shell around an inert helium core. So what you see here are basically the structures of these different kinds of stars. For stars in the mass vicinity of the sun, as you can see here, the core and the region just around it is radiative, and the outer envelope is convective. Whereas for stars above about 1.15 to solar masses, the cores of those stars are convective, and the outer envelopes are largely radiative. They can still have small convective envelopes in this mass range. Both of these kinds of stars, after they have exhausted their supply of hydrogen fuel in the core, evolve off the main sequence onto the eponymous red giant branch, and these stars start to burn hydrogen in a thin shell around this inert helium core, and the outer envelopes of these stars also tends to be convective in nature. So let me briefly touch on the life cycle of different kinds of stars. For the low and intermediate mass stars that we will be talking about in this, mostly in this presentation, these stars end up shedding much of their outer layers, and they end their lives as these outer layers basically form what is known as a planetary nebula around a very dense core, and this core is what is known as a white dwarf. For the high mass stars, they end their lives in a much more spectacular fashion, specifically for those stars that are, when I talk about high mass, I mean for those stars that are 8 times the mass of the sun and above. These stars normally end their lives as core collapse supernovae, and the reason why they do that is because they are so massive and so large that the internal temperature is high enough that they can continue to fuse heavier and heavier elements until the cores of these stars becomes iron. Now, the thing about iron is that more energy is required to fuse iron than it releases after the fusion. So because of that, it is largely inert, and once the core, the mass of the iron core reaches what is known as the Chandrasekhar mass, it is unable to support its own mass, and it collapses in on itself, and to a neutron star, basically when the electrons and protons combine to form neutrons, or in the extremely high mass case, more exotic objects like this black hole, stellar mass black hole over here. So one of the similarities between terrestrial and celestial stars is that both kinds of stars can be found in binary systems. And for the case of terrestrial stars, binary systems are what are known as couples. For celestial stars, in this case, these stars are thought of to form from the same gas cloud. They therefore have the same age and the same initial chemical composition. The orbits, as you can see from these two animations here, can be anything from circular to the left and eccentric to the right, and anything in between. The individual components also don't have to be the same mass. They can be of significantly different masses. And I may not have mentioned this in the previous slide, but I should have mentioned that the higher the mass of the star, the more quickly it evolves. This is because the nuclear reactor, let's call it, at the center of the star becomes exponentially more efficient at burning nuclear fuel, and therefore they spend much lower times in the main sequence, or basically in any other sequence. And it can be many orders of magnitude in terms of age. One solar mass star has a main sequence lifetime of 10 billion years, whereas a 10 solar mass star has a main sequence lifetime of 10 million years. So that's many orders of magnitude lower. Another interesting tidbit that maybe I should inform you guys is that these, the higher up you go in mass, the more likely it is that you will find a star to be in a binary system. Now, I think for terrestrial stars, this is probably not the case, although that could be an interesting exercise, I would have to say. Maybe we should commission someone to do that study, comparing the mass of couples and the chance that they are a couple. Anyway, let's move on. So the stars that I work on specifically are what are known as regular stellar variables, meaning that they show what is called stellar pulsations. These pulsations are basically standing waves on the surface, and these propagate within the interior. These pulsations are described by what is known as spherical harmonics, where we have these are described by three principal quantum numbers, one being the radial order n, which describes the number of nodal shells within the interior of a star. A node is basically a point on a wave where the medium in which it propagates does not move. So a nodal shell is basically a three-dimensional surface that describes a part of the interior that does not move during the propagation of not the propagation, during the as the wave continues to move. The next principal quantum number that describes the spherical harmonics is the degree L, which refers to the number of nodal lines on the surface of the star, and the azimuthal order M refers to the number of nodal lines passing through the poles of the star. So you can see these animations of how these modes look like on the top. These are obviously highly exaggerated. Some of them look like crazy alien objects, alien dancing things. But what I want you to observe is that in the bottom right, you see two diagrams of spherical harmonics. You have a L equals to 3, M equals to 0 mode, degree of 3 nodal lines on the surface, but 0 nodal lines passing through the poles. For an L equals to 3, M equals to 3 mode, 3 nodal lines on the surface, all 3 passing through the poles. So all of you are now experts in stellar evolution, binary stars, pulsating stars. So I'm sure you'll be able to understand whatever comes next. I have faith in all of you. But the point is, what is my contribution to the literature? Where is the problem? What is it that we are trying to solve? Well, the issue is that it has been long known that there are discrepancies between the observations and theory. Now, what you see here is a HR diagram, as you have seen before, but in this case, we have basically a number of evolutionary tracks. But there's something strange about these evolutionary tracks. You can see, so the masters of the evolutionary tracks are at the bottom of each track, and this is known as the zero-age main sequence, or ZAMS, where the star starts to fuse hydrogen into helium. Now you can see for those stars with mass of 1.2 solar masses and above, there are two different evolutionary pathways that this can take. So what is the difference between these solid tracks? So the blue parts of these tracks is the main sequence. What is the difference between these solid tracks and these dashed tracks? Well, the difference is that there is a different amount of internal mixing for the solid tracks and the dashed tracks. And the dashed tracks have more internal mixing than those of the solid tracks. So what happens is that more nuclear fuel, more hydrogen is introduced into the core of these stars. These stars, as I mentioned before, develop or have convective cores, and therefore the introduction of additional fuel into the core region makes them live longer on the main sequence. And this obviously propagates later on to, say, for example, here on the red giant branch, which is marked in red for obvious reasons. So it is, when you are unsure of the age of the star on the main sequence, this will obviously propagate further on in the evolution. So it has been thought that one of the major issues, specifically for intermediate mass stars, that cause the discrepancy between the observations and this theory, the theory of stellar structure and evolution, is that the interior mixing profiles are not well calibrated. So what do these interior mixing profiles actually look like? So these are examples of interior mixing profiles of a star with a convective core and a radiative envelope. So the gray regions represent the amount of mixing that's going on in the convective core. And as you can see, it is very high. And this shouldn't be surprising to you. A convective core is akin to a pot of boiling water. If you were to, say, pour in a little bit of dye, it will immediately suffuse throughout the entire volume. So that is the reason why the core mixing is so high. Now, the blue regions here are the convective boundary mixing regions. Now, this is basically an approximation of the behavior of convective fluid elements, because these fluid elements have inertia. So when they reach the convective boundary, they do not stop immediately. Instead, they overshoot into the surrounding medium. So there is some level of mixing into the surrounding medium that is typically not taken into account. So this kind of convective boundary mixing is implemented to approximate this behavior for our models. This, of course, introduces additional fuel into the convective core, and it enlarges the effective size of the convective core. Now, the red regions represent the mixing that is occurring in the envelope. This can be just for the leftmost example is just a constant amount. So, and the right, the profiles on the right show the different kinds of mixing that occur because of different physical mechanisms from simulations and other things. Of course, calibrating and differentiating between these different mechanisms is a whole study in and of itself, and it is currently ongoing work. And these envelope mixing mechanisms also affect the lifetime of the star because they are coupled to the convective boundary mixing region and therefore to the convective core itself. So the more mixing you introduce in the envelope, you will also extend the lifetime of the star. So We know that we want to look into the stellar interior in order to figure out what's going on. How can we figure out how much mixing we should introduce into the star? But unfortunately, we cannot. The exterior of the star, the photosphere, is opaque, and you cannot do that. But as I mentioned before, some of these stars show pulsations, and these pulsations propagate within the stellar interior. So the field of astroseismology, which was created, which represents the study and interpretation of stellar pulsations, allows you to figure out what's going on in the interior from the study of the pulsational behavior of these stars. In this case, you would see light and radial velocity variations on the surface. From the interpretation of these variations, you can actually deduce the interior structure and interior mixing profiles, because these pulsations propagate within the interior. So by confronting the observations with what is predicted by astroseismic theory, you can effectively extract or put good constraints on these interior mixing profiles. Now, these pulsations, stellar pulsations in general, are divided into two broad categories, and this is based on the dominant restoring force of these modes. The first category is called pressure modes, which is what you see in the bottom left plot over here, and these modes tend to propagate within the stellar envelope, typically. The other category of modes is called gravity or buoyancy modes, where the dominant restoring force is gravity, and these tend to propagate within the deep stellar interior here and here. Now, what is the difference between these two diagrams? Well, let me start by saying that a gravity mode can only propagate in a region which is stably stratified. So what you see in this middle plot here is the gravity modes that propagate in a one solar mass star, so a star like the Sun. These modes never quite reach the surface because the envelopes of Sun-like stars are convective and therefore not stably stratified. Therefore, in order to see these gravity modes on the surface, you would have to study stars with minimal or no convective outer envelopes, such that the gravity modes can propagate all the way from their convective boundary to the surface, as you can see here on the right. Now, because we want to deduce the entire mixing profile from the convective boundary, it is ideal to study stars that display gravity modes, and we study intermediate mass stars and higher mass stars for that reason. So, astroseismic theory predicts that for a non-rotating star consisting of a convective core with a homogeneous radiative envelope, G modes form patterns that are equally spaced in period in the so-called asymptotic approximation, meaning that the radial order of the mode is much higher than the degree of the mode. Now, obviously, real stars are rotating, and they are probably chemically heterogeneous. So you see the deviation from this idealized pattern in the form of a slope, the gradient of which gives the near core rotational frequency and velocity, and the dips in the period spacing pattern that you see here represent the chemical gradient, with deeper dips implying a steeper chemical gradient. So through confronting the theoretical predictions of the models with the observations, as you can see here, you can basically deduce what's going on in the interior. Now, another way in which you can deduce the interior mixing profiles is through the use of binarity. But then you might ask, well, how do you do that? It's just two stars. I mean, yes, two stars are better than one, but what does that mean? Well, as I said before, more than half of all stars are in binary systems, more than half. And the thing about binary stars is that their orbits are described by Kepler's laws. So that means that you can put constraints on the masses of the individual components. Now, if you combine that with binaries that show eclipses, as you can see here on the left, you are basically able to extract the component masses and radii to extremely high precisions. I'm talking about, in the best of cases, 1% and better. Now, these precisions are so high that you can basically constrain the amount of internal mixing by discriminating between different evolutionary tracks that show different amounts of mixing. So from just external properties alone, you can put some constraints on what the amount of mixing should be. Instead of, well, in the case of astroseismology, you would have to actually be able to peer into the star. In this case, you're doing it from external properties. Of course, ideally, you would want to use both kinds of information. So pulsating stars in binaries, that makes a lot of sense. But the thing is, we would want to study stars that are in detached eclipsing systems, because we want to know that the influence of binarity on the pulsations is minimal. And when I say detached, I mean that the material that belongs to each component is completely gravitationally bound to itself. So in the case of semi-detached and contact systems, as you can see here on the right, there is some mass transfer going on from one component to the other, or they share mass in the case of the contact systems. These stars also display G modes and P modes and other things, don't get me wrong, but it becomes more difficult to explain them and explain the behavior and disentangle the effect of binarity from the intrinsic pulsation. So ideally, we want to study stars that are detached for these reasons. There's a huge amount of synergy between astroseismology and binarity. And the main, I would say, advantage is that it mitigates degeneracy in astroseismic modeling. Now, what do I mean by that? This period spacing pattern that you see here on the right, this can be produced by stars with wildly varying fundamental parameters. And because of that, it is useful to put some limits on the size of your theoretical model grid, because, well, then you would get a closer understanding or a more accurate understanding of what the true internal properties and the true masses and radii, the true fundamental parameters are for these kinds of stars. Now, one of the ways in which you can do that is you can perform what is known as isochrone fitting or isochrone cloud fitting. And isochrone is basically a curve that connects points on, in this case, a log G versus log TEF Keel diagram that are at the same age. So basically what you're doing here is that you are restricting the age of the models. And as I mentioned before, binary stars are at the same age. So if you fit these isochrone clouds to the individual components, you are able to restrict your parameter space very significantly and get closer to the true solution. Let's call it that. I'll go into a bit more detail on isochrone clouds and isochrones later on in this presentation. Of course, the secondary advantage is that you're able to compare directly the parameters you extract from astroseismology and the parameters that you can determine from binary dynamics. So, of course, this is a good check and balance for these kinds of stars. So many studies are out there that try and combine astroseismology and binarity, but very often these studies treat the components of the binary system or the pulsating component as if it were a single star. That is to say, they exploit all of the constraints that are available to binary systems while assuming that the effect of binarity on the system is rather small on the pulsational properties. So one of the research objectives of my thesis will be to investigate these assumptions made during the extraction of these astroseismic parameters. And of course, the secondary objective would be to confront the evolutionary and astroseismic model parameters particularly for, as I mentioned, the G-mode pulsators, where you can extract as much information as possible about the stellar interior from, to those derived from eclipsing binary modeling, so the so-called dynamical parameters that you get from modeling the eclipses of a eclipsing binary. So the tasks that are accomplished and the results that I'll be presenting in the later section would be the characterization of the effect of photometric contamination in red giant binaries. This was presented in my detailed my first paper called Two's a Crowd. The next section would be the compilation of a sample of G-mode pulsating eclipsing binaries that are detached. This was presented in the first part of my second paper, Tango of Celestial Dancers. And the last part of this, of my results, will be comparing the evolutionary and astroseismic model-derived parameters with those, obtained from observational analysis for our best target, the pulsating eclipsing binary KIC 9850387. The observational analysis was presented in Tango of Celestial Dancers, and the astroseismic modeling was performed in my recently submitted paper, The Parameter Inquisition, that of course no one expects. So moving on to the results. So red giants. Red giants exhibit what are known as stochastically excited modes. These modes are a result of the turbulent convection that's going on in the stellar envelope. And the convective motions constantly excite modes at all frequencies. However, most of these modes are very quickly damped. However, at certain resonant or eigenfrequencies, which depends on the geometry of the mode and the structure of the star, you find clear mode excitation. So that is why you see these modes coming from red giants. So in addition to the P modes, as I mentioned, you can find these kinds of stars with convective outer envelopes pulsating in P modes. What you also find is that you find mixed modes in these red giants. So these mixed modes have a G mode character in the radiative zone just outside of the core of the star, and a P mode character in the convective envelope. Now, the reason why this happens for red giants and not, say, for example, solar-like main sequence stars is because of the extent of the convective envelope that actually brings down the frequencies of the P modes are much lower than in solar-like pulsators. That brings it more in line with the frequencies of the G modes that are propagating within the stellar interior. So the closer they are in frequency, the more they are able to communicate with each other, and therefore they are resonantly coupled with each other, resulting in these mixed modes. So because mixed modes exist in red giants, one is able to unravel basically the entire mixing profile, rotational profile of the red giant from the core boundary region to the envelope. So these are quite useful objects of study. So again, what is the problem here? Well, of course, intrepid researchers such as Golm et al. Here in 2016, have studied these red giants that are in detached eclipsing binary systems. And what they found was that there seems to be an overestimation of the astroseismic mass when compared to the dynamical mass. So the origins of this are not quite clear. So we decided to go forth and investigate the potential reasons for this phenomenon. So the question we asked ourselves is, does the light contribution of the individual binary components have an effect on the extraction of the global astroseismic parameter nu-max? Now, what is nu-max? Nu-max is what is known as the frequency of maximum oscillation power. And this refers to the center, the frequency center of the Gaussian that is used to approximate the pulsational signature of a red giant, or in fact, any solar-like star. So what you see here in the top, or the only plot, is the pulsational signal in the power spectrum of a red giant. It has this very characteristic comb-like structure with modes at very specific frequencies that are separated by in a very sort of systematic way. The center of this Gaussian is called the frequency of maximum oscillation power. But the reason why it is useful is because this quantity is related to the mass and the radius through what are known as asteroseismic scaling relations. So this is one of the inputs of the asteroseismic scaling relations, and therefore any issues in any systematic offsets in extracting the value of nu max from the light curve would result in a systematic offset in the mass and radius of the red giant. So we decided to investigate this particular parameter. So how we decided to go about this is we basically decided to synthesize light curves and power spectra of red giants. But how do you do that? So what you see here on the left is the pulsational signal of a red giant in the power spectrum. And what you see here on the right is the background signal. Now, the background signal is a result of white noise and what is known as the stellar granulation. Granulation is this sort of grainy-like property caused by convective cells kind of blooming and falling inwards again. It gives it this kind of grainy property that has this very characteristic slope. So in order to get the light curve of a single red giant, you would have to combine this the pulsational signal and the background signal together, and you get the power spectrum here of a single red giant. These single red giants are then combined according to their luminosities. So because we have from the models the masses and radii, and then we just combine them together based on their luminosities to get binary red giant light curves. So even in the single red giant case, so what we did was we basically we investigated if we could recover the parameters that we put into our light curves. So what we found was that even in the single red giant case, there was a systematic underestimation. So not an overestimation. Goldman all found an overestimation, but we found an underestimation of nu max compared to what we put in from these scaling relations. And the reason for that is because our inputs, as you can see here on the right, had additional power in the region below nu max than above it. So they are asymmetric. And because they are asymmetric in the negative direction, what we get out of it will also be asymmetric. So that is the reason for the underestimation of nu max. Now, we also tested just fitting the pulsational signature and also including the entire, basically both the pulsations and the granulation. And we found that granulation basically functions as a randomization element. It shifts so the dots connect two models, one which is just pulsations and the other one that is pulsations and granulations. And you can see that they basically just randomizes the pattern and increases the overall scatter of the extraction. So now that we have established a baseline for our single red giants, we asked ourselves, we decided to do the same, but for our binary red giant light curves. And we found that in most cases, the light contribution of the individual binary components has no effect on the extraction of the global asteroseismic parameter nu max. We basically are able to recover the same parameters that we would in the single star case. And the only exception to that is what you see here in the middle, where you have a large amount of scatter. This is because we are basically fitting the power spectra of red giants with two very similar red giants, and these power spectra basically overlap. And because we don't use any constraints on the nu maxes of the individual components, in some cases the overlap might be too great, and the extraction of the individual component nu maxes is completely bunk. And outside of this scenario, we get very similar results to the single red giant case. So what this means is that the results of Goldman et al., when they found a systematic overestimation, it is basically unrelated to the effect of light contribution on the extraction of the global asteroseismic parameter nu max. However, it should be noted that this light contribution still has an effect on other parameters that go into the theoretical scaling relations, such as the effective temperature, because that you would get from spectroscopy. And in order to get a effective temperature, measurement, one would have to find some clever way of either disentangling the component spectra of the binary red giant, or other sorts of trickery. And of course, the light contribution would affect that for sure. So now we move on to the meat of my thesis, I would say, where we attempted to compile a sample of G-mode pulsating binaries. And the reason for that is that only several tens of these kinds of stars have been found so far, and only 4 have been studied in any sort of detail. So what we did was that we attempted to find more of such targets by mining the Kepler eclipsing binary catalog. We basically took all of the detached eclipsing binaries from that catalog. We pre-whitened the light curves of those stars. We pre-whitened the light curves with the first 1,000-ish orbital harmonics, and we looked at the residuals in order to see if there was any signature of G modes or G mode period spacing patterns. Obviously, we can see that in the plot over here, where the original Fourier transform in blue is completely dominated by the signature of the eclipses. So what we found overall was that out of the 299 detached eclipsing binaries that we selected from the catalog, 93 of them were found to exhibit G modes, 48 of which were completely new, undiscovered. However, we only found 7 out of these 93 that we would consider to be decent candidates, and only 2 of them we would consider to be good candidates. And by good, I mean these candidates displayed period spacing patterns of more than 6 radial orders, because we need a large number of radial orders in order to do a proper characterization of the internal properties during astroseismic modeling. What we did also is we did a statistical characterization of the sample. We plotted the pulsational parameters, basically the number of independent frequencies versus the frequency and the frequency of maximum oscillation amplitude, to n int and f max, versus the orbital period, the eccentricity, and the effective temperature. And we found actually minimal correlation between these pulsational parameters and the orbital and fundamental parameters of the stars. We noticed that our method of trying to discover these G-mode pulsators was rather brute force. So we also compiled an additional short list of 23 stars, which have a high G-mode density, that are probably worth a second look to see if these could be astroseismically viable. Overall, in this whole process, what we identified was that the eclipsing binary KIC 9850387 displayed not just one period spacing pattern, which you can see here. This is an L equals to 1 pattern, but it displayed 2 period spacing patterns. This is unusual even for single stars. You will also notice from this period spacing pattern is that it is rather flat and with no clear dips. So as I mentioned before, the gradient of the pattern implies something about the near-core rotation. So in this case, the near-core rotation is very, very small. And the lack of dips implies either that the star is very young or that the star has a high amount of internal mixing. And we will investigate that during our subsequent deep dive analysis. So now that we've identified our best candidate, we went forward with an in-depth observational analysis. We performed a spectroscopic follow-up. We got Hermes and Keck spectra, extracted the radial velocities from these spectra. We performed spectral disentangling, and we were able to derive the atmospheric parameters and abundances of the primary star. And then we did an iterative sort of modeling with the atmospheric analysis to determine the masses and radii of the individual components. What we found overall was that the system was in fact a main sequence double-line spectroscopic binary. This was in contrast with the claims of some other authors, basically Zhang et al. In June of last year, where they mentioned that it was a SB1 system. So we proved that claim to be false. We also found, in addition to the G mode period spacing patterns, we also found a number of high frequency modes that we initially thought to be P modes, and these would be analyzed in when we perform our astroseismic modeling. So the next step, now that we have all of our observational data, we have our high precision dynamical masses and radii, would be to perform evolutionary and astroseismic modeling of the star. So to do that, we would use the technique of isochrone and isochrone cloud construction. In this case, what you see here on the left is what is known as an isochrone, which is a curve connecting points on the HR or the Keel diagram. And the Keel diagram is the log G versus log TEF diagram that connects points that are at the same age. So what we want to do is we want to investigate the internal mixing in the star, or basically in the primary star. So I should have mentioned the pulsations that originate in the star, in the system, are coming entirely from the primary star, because the secondary star was found to be solar-like, and if it were pulsating, the frequencies would be much higher and therefore distinct from the frequencies that we observed for this star. So the frequencies that and the low frequencies that we observed would have to come from the intermediate mass primary star. Anyway, back to the isochrone clouds. In order to investigate the amount of internal mixing, we would have to basically group isochrones that come from models with different amounts of internal mixing together into a single group. So what you see here on the right is an isochrone cloud where all of the points correspond to models at the same age, but with different amounts of internal mixing. Now you can see something strange where at the higher mass end, it seems to break apart. And the reason for that is because we use a logarithmic scaling for the amount of envelope mixing in the model. This is because we thought, well, from the very flat period spacing patterns, we suspected that it could have a very high amount of envelope mixing. And so we decided to include very high amounts of envelope mixing in the logarithmic scale, and at the higher end of the scale, this causes basically the evolutionary tracks to deviate very significantly. This results in so-called these evolutionary tracks that really go off into the distance. So with our isochrone clouds in hand, we basically fitted the positions of the individual components in the Keel diagram. The red curve here is the best fitting isochrone cloud. The pink regions are the 95% highest posterior density of the fit, and the black regions represent those models that agree, in this case, with the primary and with the secondary mass. Now, what you can see here is that the secondary mass seems to be in good agreement with the dynamical position of the star in the Keel diagram. However, for the primary star, there seems to be a slight discrepancy, and the reason for this is because we used evolutionary models at a fixed metallicity, which is derived from spectroscopy. If we also included a range of metallicities corresponding with the spectroscopic errors, this discrepancy would disappear entirely. However, if we include metallicity as another free parameter, it introduce additional degeneracy to an already degenerate problem, which is the problem of astroseismic modeling. And therefore, we chose not to do so for our future astroseismic modeling attempts. So for our astroseismic modeling, we decided to use two different merit functions. We used the chi-squared, which is basically a squared deviance metric of the observations and theoretical predictions. And we also use what is known as the Mahalanobis distance, which is a maximum likelihood point estimator that basically takes into account the theoretical uncertainty in the model grid through the use of the variance covariance matrix V. Now, this matrix lambda is the squared errors, and y theo and y obs are the vectors representing the theoretical predictions and observed vectors respectively. So we compared these two different merit functions, and we also use two different kinds of astroseismic observables. We use the quantity pi-naught, which is related to the Brun-Weiser or buoyancy frequency, and the extent of the G-mode propagation cavity defined by R2 and R1. And we also use the period spacing values directly. So these are the delta PL values. We generated theoretical period spacing patterns using the stellar pulsation code Gyre, and therefore we were able to confront those to our observed period spacing patterns. So here are the results for modeling using pi-naught. This is a rather complicated diagram, so I'll try and explain it as best I can. So the dotted box you see here is a result of using the 3 sigma intervals, or the 3 sigma intersection of the dynamical mass, the dynamical mass, the dynamical log G, and the effective temperature from spectroscopy. And this region is necessarily very small because, as I mentioned, the precision of extraction of the dynamical parameters is very high. The idea was to have constraints that were intermediate between this very, very small parameter space and the extent of the full grid that is defined by the 95% highest posterior density interval of the Isochrone cloud fit. So what we did is that we fit the disentangled primary component spectrum as if it were a single star, basically ignoring information from the eclipses. So we were able to extract a second set of atmospheric parameters and basically a log G and a effective temperature estimate. The X here refers to the position of that star based on the spectroscopic, the so-called single star spectroscopic parameters, and we took the 3 sigma interval of that to have a second set of constraints. The blue, the red, and the green data points represent models that were the positions of the best fitting models for the full grid in blue, the so-called single star spectroscopic grid, the restricted grid in red, and the so-called dynamical grid, which is this small dotted box region in green. So the different symbols represent using either information from the L equals to 1 mode, or the L equals to 2 mode, or a combination of the L equals to 1 and L equals to 2 mode. So what you see here overall, it doesn't really matter what the different symbols are, but what I want you to take away from this very complicated plot is really that there seems to be a good agreement between the dynamical position of the star and the results from modeling using pi-naught. Of course, with very large error bars, unfortunately. This is because we are using a single parameter, a single variable to estimate multiple free parameters, the extent of the core boundary mixing, the age of the star, so basically the core hydrogen content, and the extent of the envelope mixing. And you can see that placing increasing amounts of constraints basically only improved the precision, and it basically brought it closer towards the dynamical position of the star. However, when you're modeling using the delta PL, basically the period spacing patterns, the results are all over the place. So it varies depending on whether you're using a chi-squared or an MD merit function. It varies depending on what the size of the grid that's used. And while it seems that there's still a reasonable agreement between the different sets of parameters, the results are not great. The error bars represent 68% highest posterior density. So these are 1 sigma error bars. So there's a difference between what you use. But overall, the results for using the period spacing pattern values is superior in terms of precision when compared to using pi-naught as the astroseismic variable in question. So the Mahalanobis distance tends to select models with poorer visual fits rather than the chi-squared. As you can see for the chi-squared, regardless of what grid was used, and regardless of the size and extent of the grid, the best fitting patterns are more or less the same. Whereas for the MD, because it is incorporating the variance in the grid, it selects preferentially. I won't say preferentially, but the best fitting models tend to have values that actually deviate quite significantly from the observed patterns. Overall, what we find is that we find higher than expected levels of internal mixing in our star. That could be a result of this could be a result of tidal mixing. However, we also see similar behavior in single stars, and so in that case, this higher than expected levels of internal mixing could be an intrinsic property of the star. So we also found some high frequency modes in our frequency spectra, as mentioned before. Using our best fitting model, we calculated the theoretical frequencies, and we were able to find that we found a L equals to 0 mode, so a radial mode, and a L equals to 1, N equals to 1, so a low order G mode in this frequency regime, but they were offset from the nearest peaks. We posited that this is a result of the so-called surface effect, which affects which tends to be quite common for solar-like pulsators. Intermediate mass stars, such as the primary star of KIC 9850387, would also have a small convective envelope, and therefore this explains this offset, and it was also found in other similar stars. This high amplitude doublet that you see here on the right is because we theorize that it is potentially a L equals to 1 doublet that has been rotationally split, so with a missing zonal mode. So you have a M equals to 1 mode and a M equals to -1 mode with a missing M equals to 0 mode. And this splitting is sensitive. It indicates the amount of envelope mixing, because in fact these low order G modes have a maximum in terms of the rotational kernel, which indicates its maximum probing power, much closer to the surface as compared to the very high order G modes that have maximum probing power closer to the core. So the rotational splitting of the G1 mode, the low N G mode, it implies a low level of envelope rotation. However, we find the way that we calculated our projected rotational velocity, we use the projected rotational velocity as a proxy for the total broadening in the stellar spectrum. Therefore, and what we found was that if we fixed the projected rotational velocity and allowed the macroturbulent velocity to vary as a proxy for the pulsational broadening, we actually find very similar, qualitatively very similar results. So it is possible that the envelope and the surface could also still be rigidly rotating. I'm going to stop here. I will leave you with my summary and conclusions. And for the future work, I will, the idea will be to try and find more promising candidates using, say, space missions such as TESS and Plato. The issue here is that less than 4% of all eclipsing binaries were found to be astroseismically viable. And the other future work for this kind of research would be to automate parts of the observational analysis, which takes a lot of time, and also using non-adiabatic, maybe advancing non-adiabatic astroseismic modeling, because that would significantly increase the sample size if we were able to get it to be broadly applied. So thank you all for your time.
Thank you, Sanjay. We will now move on to the discussion part of this session. First of all, let me introduce the members of the examination committee. First, we have Connie Arts from the KU Leuven Institute of Astronomy. Then we have Andrew Tkachenko, who's the main supervisor of Sanjay and is also from the KU Leuven Institute of Astronomy. I am myself Thomas Kokolios, chair of this examination committee from the KU Leuven Institute for Nuclear and Radiation Physics. We also have Peter de Cat from the Royal Observatory of Belgium, Pablo Marchand from the KU Leuven Institute of Astronomy, and Rich Townsend from the University of Wisconsin-Madison, who could join us in spite of the big time difference. We are very pleased to have you here, Rich. Finally, there is also Uksana from the KU Leuven Institute of Astronomy, who had to be excused today. However, he did take part in the first examination that Sanjay did a few weeks ago and participated very actively in the questions at that time. So now I will first ask some members of the examination committee to share their questions with Sanjay, starting with Rich Townsend.
Hi, Sanjay. Thanks very much for a lovely talk and very well presented.
Thank you very much.
I've got actually a question about your, I guess, your penultimate slide where you show the rotation measurements for KIC 9850387. Do you have a sense of what the error bars are on the core and envelope rotation rates?
They are tiny. So the core rotation rate was taken from Gang Li and collaborators, and they are both smaller than the symbol size. So
okay, so
the reason why they're not on there, it's not a mistake or something.
Sure,
like that.
Sure. Yeah. So that then raises an intriguing question of why the core rotation is slower than the envelope rotation, because naively I would imagine it to be the other way around, that the envelope would be more slowly rotating because it's expanded, it's very large, and so if it has comparable angular momentum to the core, it should be much more slowly rotating. So do you have any thoughts on that?
Well, my thoughts that it could be because of perhaps angular momentum transport from the core to the envelope due to, say, internal gravity waves, for example. So that actually causes the core to slow down, and then that results in the envelope being more quickly rotating than the core. So that is what I would suspect as the reason for this mechanism.
Okay, and is there any possibility that the binarity could have an influence, or are the stars just not close enough?
Well, it could have an influence, certainly. I mean, I don't discount the fact that this could be basically some sort of a tidal friction mechanism operating on the deep interior. But we also I think a similar behavior was also observed for another eclipsing binary system. Sorry, lost my train of thought there. It's possible. I mean, what I'm trying to say is that it's certainly possible that that the tidal mechanisms are the reason for this discrepancy. Let's call it.
Okay.
Yeah, well, actually, no. This is what I wanted to say. Sorry, is that the surface rotation rate is also discrepant from the orbital frequency, and that is a reason why you would think that there would be some sort of synchronization with the orbital frequency, but that is also discrepant.
Okay. Yeah.
So that's the reason why it could. I mean, it could be certainly, but you would expect more correlation to give it more credence as a mechanism.
Okay. I do have one other question.
Yes.
So I think your analysis has demonstrated that the mass discrepancy between astroseismic and binary masses, the sort of offset, is not attributable to the binarity. So do you have any feelings about where we should be looking for the origin of this discrepancy?
Sorry, the discrepancy. So in the case of the G-mode pulsators, you were saying?
I think early on slide you highlighted the fact that dynamical masses and seismic masses.
For the red giants, you mean?
Yes, the red giants.
Yeah. So the result of gold metal.
Yeah.
Right. So I mean, what I mentioned before was that it is not due to the effect of light contribution on the extraction of the parameter nu max. That is not that we are, of course, ignoring the effects of tides and other things. This is pure light contribution. So this effect could still be binary.
Okay.
Yeah, very much so. It is just not based on light contribution specifically. It also could be, the effect of light contribution on the on the determination of the effective temperature, which is done, via spectroscopic analysis. So.
Okay.
Yeah.
Thank you.
Thank you very much.
Thank you very much, Rich. Then the next member of the examination committee would be Peter de Cat.
Yes. Well, first of all, I would also like to congratulate you with your work and with your thesis, which is very well written. I think I read it with a lot of pleasure. So,
Thank you very much.
I also have two small questions. And my first question is actually related to one of the last slides that you showed, which was dealing with the high frequencies that you found also for the star that you were studying in chapter 4. So one of the lowest frequency you interpret in your model as as a radial mode, as the fundamental radial mode, and two of the other frequencies were interpreted as components of a rotationally split L=1 mode. But how do you interpret the fourth frequency there? Because you had actually 4 frequencies there.
Indeed. So there's clearly there's clearly a missing frequency. How would I interpret that one? Well, I'm actually not sure why it's there, to be honest. Well, the models don't predict it, but that doesn't mean that necessarily that I mean, it's there. Obviously, it's we've taken care to ensure that we selected only those frequencies that were not combinations. It could still be a combination. It could be a very high order combination frequency, for example, and therefore not real. But yeah, other than it being a very high order combination and therefore basically a mathematical artifact, yeah, I don't really know what this frequency would be.
Because it was also rather close to one of the harmonics of the orbital frequency. But yeah, the orbital frequency should be known very precisely, so I did not expect a link there either. But I still have another question about that figure, actually. So you mentioned already that there is an offset of the frequencies that you observe with the theoretical frequency that you have from the model. And you actually based this figure on one theoretical model that you considered as the best model that you found with looking at the G modes.
That's right.
But would it be worthwhile to also search for a model that better fits this fundamental radial mode and to see if how it still fits the G modes? I mean, to go from the other direction. So assuming that this low high frequency, let's say it, is a radial fundamental, try to fit it in a better way there. And to see if the model that you find is still in the family of models that you were considering for the G mode solutions.
Yeah, I mean, that's certainly possible. But then we also run into the thing of, so in this case, you would basically assume that there is no surface effect then.
Okay,
right?
Yeah.
But I mean, it's possible that there is no surface effect. That's also a possibility.
Because
yeah. But
my main question is basically how solid is the other conclusions that you draw, especially about internal rotation rate, do you think if you would search for a better model that would fit the high frequencies better, that it would have a large effect on the conclusions of the internal rotation or not?
So when you talk about internal rotation, because these are the low order G modes, right? And they are basically they probe basically much more in the envelope.
No, but I'm still talking about its high frequency. So if you would search for a model that better fits the fundamental radial mode, my question is basically, do you think it will have a large effect on the rotational rate that you determined in the next step of your analysis? If you understand the question.
Yes. So, but that depends on the Ledoux coefficients, right? So I suspect that won't have a. I mean, they do not vary significantly in the high frequency regime.
Okay.
So I suspect not. You won't have you won't have a huge effect on the what you get for the envelope rotation.
So, and I have another question, something different. So for this analysis, you were focusing on the Kepler data to search for your candidates, and you already mentioned in your future prospects that you would also like to look at missions like TESS, for example. But would it be worthwhile to look at K2? And do you think it might be possible to also link this satellite data with ground-based surveys in one way or the other to find additional candidates?
So, I mean, one of the troubles with K2 is, of course, the limited resolution of the data set due to its much shorter time base. So
a similar problem you will have with many of the stars that are observed.
With TESS also has there's a similar issue. I mean, certainly we want to find as many candidates as possible. Whether they would provide the same level of astroseismic inference is something else. Again, the work that I presented is merely just a first step. We want to see if we can really find many more of these candidates, and maybe we can get some statistical analysis going to see where the issues are. I mean, this all the reason for this increased mixing and whatever, it could be just due to binarity, right? We don't know that for sure. This is really just a what's it called? Kind of a pathfinder, almost. Pathfinder mission. Yeah.
But you don't see any link to ground-based data for this type of studies?
I mean, ground-based data suffers from issues like aliasing and all that, and so finding. Again, we are limited by the adiabatic framework, and therefore we would have to look for period spacing patterns. And then with the complication of this huge aliasing, the chances of finding period spacing patterns from ground-based data would be. I'm not saying it's not possible, but it's certainly going to be much more challenging. That's my naive thought.
Okay, well, thank you. I will stop here.
Thank you, Peter. The next round of questions will be from Pablo.
Hi there, Sanjay. Thank you very much for the presentation. I enjoyed it, and also enjoyed reading your thesis.
Thank you very much. Very kind of you.
Yeah, for sure. So I had questions a bit following what was just asked in terms of your future work. So you're discussing using TESS and Plato as a potential way to find extra candidates, and that's what I find most interesting, because more or less you need lots of objects observed to make general statements about stellar evolution in the end.
Exactly.
So how do you project the sample size to increase? How many do you expect it to get to a point, for instance, where big data approach is necessary to study these sort of things, where really automatization of the process you've done is essential? What's your perspective of how things would evolve in that sense?
My perspective right now is that honestly, the automation, as I mentioned, of the various different components of the analysis is really, in my opinion, the stumbling block. And well, also because in addition to the once you've identified a good candidate, then you have the follow-up spectroscopic data that has to be found, time series, to investigate if it is a SB1 or SB2 system, and then you have the whole atmospheric analysis and the disentangling and what have you, right? And a lot of it is right now very manual. If we can automate part of this process, that will cut down the time immensely, and then you could just go straight from observations to the modeling straight away, because that chunk of time that you would spend otherwise on something that requires a lot of manual input is reduced significantly.
Okay, so if I understand right, it's more or less in the candidate identification process that the automation is more fundamental, not so much on the actually studying the final candidates, you would obtain.
No, I would say it is the no. I mean, what I'm saying is that once you've identified the candidate, so identifying the candidates is the easy part. It's just it's the subsequent steps that requires the combination of different kinds of data, iteration between the different steps, processing the raw data, things like that. These things take a lot of time, and I think I personally spent a lot of time on these steps before starting on the theoretical modeling side of it, in and of itself. So if we can shorten that time, that will basically open up a whole new world, in my opinion.
Okay, but in that sense as well, how many candidates, like a number? So you studied one candidate, you said you had like really 2 good candidates from the Kepler data. Mm-hmm. After analyzing TESS and Plato, would you say you'd get 10, 100, 1,000? What's the ballpark number one should expect for these missions?
I would. So I don't have a huge amount of experience with the TESS data, but yeah, I would expect something in the order of 100. That's what I would expect.
Okay.
TESS. Yeah.
Yeah. So I would guess it would be hard to repeat the work you've done a full 100 times. That would require many PhD students.
Oh man, that's like 10 PhDs right there.
Yeah. So yeah, just another quick question. Something you mentioned that more or less using non-adiabatic modeling would increase the number of candidates. Mm-hmm. That's something I don't understand, how the astroseismic modeling affects the number of candidates you can obtain.
So the thing is, we are basically restricted to those stars that display period spacing patterns. Now, most G-mode pulsators do not display period spacing patterns. And it is because we use the adiabatic assumption that we are restricted to this. If we use non-adiabatic computations, we can also study those stars that do not. So basically, those stars that display just a few peaks, because non-adiabatic computations would also show which modes are excited and which modes are not excited. And therefore, you expand your sample size tenfold if you just move to non-adiabatic computations. So that would be a huge advantage.
Yeah, sounds great. So I think those are the only questions from my side.
Thank you very much.
Thank you too.
Yeah, thank you, Pablo. I would like to take this opportunity to tell our audience that they may also ask their own question in the chat, and that after this final round of questioning, we'll be passing them all also to Sanjay. So don't hesitate to type them in. Next would be Connie Arts.
Yes, Sanjay.
Hello, Connie.
Thank you very much for your presentation. I would want to correct something, actually. I have to do that.
Oh, no, I expected that. Please correct me.
Well, I will tell you what. You started off by saying that you had the privilege to work for 2 supervisors. But of course, both of us know that there's actually only just one supervisor, and that's Andrew. And I want the audience to know that, and also consider you as a duet, you and your supervisor. And so actually, the habit is that supervisors don't ask any questions. But given that, I will still ask you a question right now. And before I do that, I would like to congratulate you.
Thank you
And
very much.
also actually your family and friends far away, because I would like to take us back to the day that you arrived in Leuven. I still remember that, and surely you remember that. You came from very far. You were selected because you were the most motivating student in our interviews, and that's what got you here in Leuven. And I think you will agree with me that there was a lot to learn. And we did that together.
Still learning.
That's something of very major importance to me. When people that come here, when I see their steep exponential growth, as we are all familiar with these days, well, your learning curve really was an exponential growth. That's important. I think you enjoyed that, despite the struggle at some occasions. That's very important. And I would like to thank you for bringing diversity in our institute in a very broad sense, because also that is very important to me. And I thank your family and friends from far away for having allowed that we have you with us for all those years in Leuven. So thank you for that in first instance. So having said all that, I still have a question, and I would also like to actually thank Rich for having triggered you to look at the high frequencies of your star. So as you have noticed, when you move to interior rotation of stars, then people have major interests, as your jury members had already expressed. And I also have a question there for you. So I'm a seismologist, as you know. I believe the Asteroseismology, I rely on it on a daily basis. So
yes, I believe your name's on the book, if I'm not mistaken.
Yeah. What if the surface rotation frequency of the star is not so greatly determined? Because there you use another methodology. So in analogy to Peter's question, who asked you what's the level of change that you can have on your results from the modes, even if the modes are wrongly identified. How could you perhaps move to a less differential rotation? What's the level of change you could allow there, given the way that the surface frequency was derived by somebody else, not by you, by the way. I want to stress that. Have you thought about that?
You're talking about the difference between the core rotation derived by somebody else and the surface, the envelope in this case.
Well, no, I'm talking about the surface rotation, and how that relates to the envelope rotation, and how you relied on different measurements in getting there.
Right. So, well, as I mentioned, for the surface rotation, what I did was we used v sine I, the projected surface rotation velocity, as a proxy for the total Browning. Right. So that also includes pulsational Browning. And I think I might have mentioned close to the end that if we instead fix the v sine I at a value derived from the rotational splitting and allowed the macro turbulence to vary, you get a result that is qualitatively very similar. So it very well could be that there's no differential rotation between the envelope and the surface. So that is certainly a possibility. And this is just a result of the way our methodology of doing things.
Yes, and so let's imagine that for a moment. What would that imply? Because as you have seen, this graph triggered a lot of questions. Does that change anything at all for the future life of the star if you would have rigid rotation from the envelope to the surface, or does it not matter?
Well, if there was rigid rotation from the envelope to the surface, that would imply, I guess, well, if there was differential rotation, there would be friction, right, between the layers, and so there's some and then there would be a slow down effect, and eventually the surface rotation would match the envelope rotation at some point due to the friction. But considering that the surface rotation velocity is also very small, I have a hard time seeing how that would have a significant impact on the evolution of the star, unless you are pushing me to an answer and I'm not seeing where you're supposed to be pushing me to.
For once, I'm not pushing at all. I just want to hear your opinion, okay? And so then connected to that, you have more stars. You will also be a bit longer with us for several more weeks, let's say. Let's imagine you could choose what you would want to do in these few weeks. What would you investigate?
What would I investigate? Oof, the difficult questions now. What would I choose? Well, I mean, I was working on this this triple system you grew with Cole Johnston, and that was actually a very I guess I spent maybe too much time on it, also distracting me. But I really enjoyed it because it was so unusual, such an unusual system. So if I had a choice, I would probably work on these more exotic objects. Let's call it.
Okay, so exotic binaries tell us more than usual single stars in terms of stellar evolution. Is that sort of what you're telling us?
That's not what I'm saying. Definitely not what I'm saying. It's just more fun for me personally. It's nothing to do with. I don't have a scientific agenda. I was like, oh yeah, this will be the key that unlocks the universe. No, that's not what I'm saying at all.
Okay.
This system is really cool.
Yeah. Well, with that, I think it's really important for scientists to have great fun, as you know, and so. I hope that was the case for you in the past 4 years and for the few more weeks to come. So with that, I'll hand back the floor to the chairman, thanking again your worldwide network, including your family and friends from far away.
Yeah, there's people from Texas over here. Yeah.
Good. Thank you, Connie. Would the supervisor, Andrew, have some comment or questions at this stage?
Well, thank you, Thomas. Sanjay, first of all, congratulations, with completing major milestone, as I see it, at least.
Thank you also.
And so I had a list of 10 to 15 questions, actually, but I'm afraid we don't have time for that. And because Connie mentioned that it's a habit that the supervisor does not ask questions, I'm not gonna ask you questions, and we'll pass it on to Thomas now.
Okay, thank you. Well, the chair also does not ask question at this stage. We're just making sure, as a master of ceremony, that everything goes fine, as should a good master of ceremony do. But then I would like to turn to the audience and see whether there are any questions in the chat. I haven't noticed any just yet, but maybe this is the time at which people would like to ask their burning questions. I've seen a lot of excitement and a lot of support coming from the discussion in the audience.
Thanks, guys. Appreciate all of you.
I don't see any just yet. Don't hesitate to keep posting. Those will definitely then be transferred to Sanjay, and I'm sure he'll be very excited to answer them all at a given time. So thank you very much for having participated in this part. The jury will now deliberate in a separate session, and we will come back afterwards. So please stay all connected and stay tuned until we come back for the next part of this session. Ladies and gentlemen, dear colleagues, I will now proclaim the result of the deliberation by the examination committee appointed for the doctoral degree in science, astronomy and astrophysics. Mr. Sanjay Sekaran has presented to the faculty his PhD thesis on the topic Deliberation, comparing the observational and theoretical parameters of binary systems with pulsating components, in partial fulfillment of the requirements for the PhD in science, astronomy and astrophysics, and has defended his thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of KU Leuven, I confer upon Mr. Sanjay Sekaran the degree of Doctor in Science, Astronomy and Astrophysics.
That's right, baby!
I hereby close this session, but please stay tuned as the main supervisor, Andrew Kachenko, would like to share a few words.
Yeah, so. All right, Sanjay, it's my time now to say a few words. Thanks to Thomas that he allows me to do so. Yeah.
In Tamil?
Let me start by congratulating you. Yeah? So with completing this major milestone called PhD. Yeah, and I'm really proud that I can actually call you the doctor among the first people on this planet. Yeah? So I really hope that you enjoyed this 4-year-long adventure where you had both good and challenging moments, I should say. And I'm really proud to admit that you always saw those challenges as opportunities for your personal and professional growth. Yeah. So, and although the term exponential growth entered lives of many people worldwide, and it must in negative sense, and it's the reason why we are doing this virtually today, I really want to use it positively today, that term, to describe your professional and personal development over the past 4 years, where in astronomical terms, you evolved from proto-scientist to a quite independent researcher. Yeah, as you have mentioned in your manuscript, but in different words, of course, it has been a long and winding road that ultimately led you to a right door. And I believe you have many career opportunities behind the door waiting for you. Yeah. Perhaps you don't fully realize that, but you're the first and the only one in several aspects. Yeah. So first of all, you're the first PhD student of mine who defended PhD, because all students before you I supervised in duo with Connie, and you're the only one I supervised by myself. And of course, you will always remain the first one. Yeah. So you're also the first person who ever called me a boss. Yeah, and I think you will be the only one ever calling me like that, unless somebody will start teasing me. Yeah. You're also the first Singaporean student at the Institute of Astronomy, and of course, you will always remain the first. Yeah. So far, I didn't manage to convince any of my PhD students to play basketball. Yeah? And you're not an exception here, but you're the first and the only one so far who will always be reminded about that by something that I put inside a present box for you. Yeah? By the way, the fact that you call me boss. Yeah, I also thought that it's worth memorizing that, and I also put something associated with that inside the present box. Last but not least, it's the first time ever, and I sincerely hope it's the last time in your life that you're going to hear such a horrible pronunciation in Tamil. Yeah, your native language.
This is gonna be good.
Sorry for that, yeah. And Budan Sanjay, in the Payarchayu un anubavum mikhavum orunala anubavum ne namugiren. In the amogamane neritai ni waukai maudum maraka matai. Yenake unmele mikhavum parumai aka irke. And Buddhan Sanjay ode amavum apavum. In the namildum ungaluku mikhavum perumai nireinta neranme nan nabugiren. Unhau payan or doctor patam vanhi vitar. Unhaluke nan rombe nandri kuru giren. I hope it was not that terrible and you could understand at least something from that, and I hope that your parents could also understand at least something from what I just said. I must admit it's not the most easiest language on this planet. So Sanjay, you probably noticed that some of the jury members wore a gown for you today. Yeah. Unfortunately, I didn't have that possibility. I don't have one, so I decided to at least wear this natural hair hat, yeah, for you today. Okay. So once again, Dr. Sanjay, big and sincere congratulations to you. Please enjoy this moment, and there is a present box waiting for you over there at the proper social distance for after the defense. Okay. So I think I will finish here, and I'll give the floor back to Thomas.
Thank you, Andrew, for these very kind words. Sanjay, would you like to do something before we close this session completely?
Yes, I would like to also say a few words to thank the people who have, in some way or other, brought me to this point. I mean, honestly, if you had told me, 5 years ago, 6 years ago, that I would be doing a PhD, I would say that you were out of your damn mind. And this astronomical journey was a complete and utter experiment on my end, because astronomy is not taught in Singapore, and this was just somewhat of a childhood dream of mine. And I thought, hey, let's give it a shot, see where it takes me. It's taken me here to the end of my journey to this PhD. And I've experienced a huge variety of different experiences, both good and bad, and they've all taught me something in this entire journey. I've made lots of friends. I've experienced many things, And the other thing is that I would like to thank, of course, Andrew, for being there for me. I know I've not been the ideal student, far from it. In fact, I appreciate your patience with me. I knew that I had a lot to learn. Certainly at the beginning, I was wondering why I, wasn't getting what I was supposed to get. In a sense, I wasn't getting the point of all of it. But I hope I've gotten at least part of it, and I'm quite happy that I've been able to complete the journey, and I've gotten to this point. So personal growth is certainly very important to me, and I'm very happy to be surrounded by such wisdom and people who have this kind of patience. Of course, I would be nothing if not for my friends and my family. So this achievement is dedicated to my recently deceased grandmother. She left us last year in July, and I hope that that she's proud of me. And of course, my parents, my friends back in Singapore, here, Germany, Paris, the US, everywhere, and some of you are even in this live stream. I'm grateful to have met all of you, and I could not have done this without all of your help and guidance. I also want to thank the Connie, of course, the grand matriarch of the of the MAMSI team for her kind of guidance and her support at all times. And of course, certainly the members of the MAMSI team, all of you have helped me to figure out one thing or other. And I would like to thank the Cole train, Cole Johnston, for helping me out. Try at least when in the very beginning when I had no idea how to do anything. You've really come through for me, man. And couldn't have done this without you. I'm really grateful for your help. My bandmates in Swan, in Moonwave, yeah, all of you guys, and my bandmates back in my ex-bandmates back in Singapore, and my friends, yeah, all of you have helped me in one way or another to get to this point. This achievement is not just mine; it is for all of us. At least I'd like to think so. I get the title though, but you can share in the achievement.
Okay, thank you very much, Dr. Sekaran. And with this, I would like to finally close this session. We would have very much liked to continue this informally around a drink and some nice food. Unfortunately, the situation does not allow us to do that, but we will certainly all celebrate in your name tonight. Thank you very much. Goodbye, everybody.
Bye, guys.